I hope you enjoy it, even remotely. And today Rodrigo had an appointment, so I'm taking over as the microphone holder. So please, Professor Carlos, go ahead.
Okay, thanks very much. So let me share my slides. All right, so hello again. Um, Yesterday we finished by pointing out that all observations that we currently do in cosmology and all the subsequent data processing is one way or the other model dependent. It has some hidden assumptions or even explicit assumptions. Um, and we asked ourselves, what is the most model independent assumption we could ever hope to do in cosmology? And I told you that the answer to that question is something called redshift drift. So my task for about half of this last lecture is to explain to you what is the redshift drift and how you can measure it. So uh, the idea is extremely simple. A 14-year-old can understand it. I've tried it and it works. So the idea is the following. So you go out tonight, you look into the sky, and you look at a distant object which is just following the cosmological expansion. That object is at some redshift. If you go out again tomorrow night and look at that same object following the cosmological expansion, that object will be at a slightly higher redshift because the universe has expanded a little bit between tonight and tomorrow night. If you can measure this difference, then what you're doing effectively is seeing the universe expand in real time. So that is the redshift drift. It's a direct, model independent measurement of the expansion history of the universe. And if you think about it, it's it's independent of any assumptions on gravity, on the geometry of the universe, on clustering properties of matter, anything. If you do it spectroscopically, just with one line of sight, it's basically that there's no hidden assumption in it. If you combine data from different lines of sight, then you might already be doing some assumptions on homogeneity and anisotropy and so on. But in principle, conceptually, it's a model independent measurement, mapping of the expansion history of the universe. If you want to think of it at a more conceptual level, this is different from any other observation in cosmology because you're not mapping our present day past light cone. What you're doing is directly comparing two past light cones from two different epochs. So this is the conceptual difference between redshift drift and any other observation. And the expression for the redshift drift is very simple. It's the equation you see on the screen. So the change in redshift of this object following Hubble flow in a given time interval dt is just given by the right-hand side of the equation. And obviously, h of z, the Hubble parameter, encodes the impact of the cosmological model in question. So the drift will be different for different universes, different expansion histories. So this plot that you see on the right comes from the Linsky et al. Paper in 2008, gives you some idea, some examples of how the redshift drift changes as a function of redshift. And the important point, among others, is that in a universe that only has matter and radiation, such as the case with the blue curve, the drift is negative at all redshifts. It's not constant in redshift. It starts out at zero by definition at redshift zero, and then it becomes more and more negative as you go to higher redshifts, but it's always negative. In a universe that is accelerating at the present day or close to the present day, you get something like the red curve. The drift starts out at zero, it becomes positive, then it goes back to zero, and at high enough redshifts, it becomes negative. So one important point is that a positive drift is an unmistakable proof of acceleration and a proof of the presence of dark energy. And the diagram illustrates a little bit how you could use the redshift drift to to discriminate, to test between different cosmological models. So you take your preferred cosmology, let's say Planck cosmology, Planck lambda CDM with the with best fit parameters, and that model will predict a specific curve somewhere in this parameter space for the drift as a function of redshift. So it predicts a value of the drift at any redshift, and then you can go out and measure it and check whether or not this is the drift you find at the appropriate redshift. So conceptually, this is all very simple. The difficulty, of course, is that the time scale for the evolution of the universe is much, much larger than human lifetimes. So the magnitude of the signal that you expect for, let's say, flat lambda CDM Planck cosmology is a few centimeters per second per decade. So if you want to do this as a spectroscopic measurement, you need a spectrograph that is precise and accurate and stable to this level. Because if you're not going to do this measurement from one night to the next, but you may hope to do it in a time scale of a few years. And actually, the interesting thing in this case is that the signal grows linearly with time. So the more you wait between the first and the second epoch, the more your signal increases and the easier it is to detect. So in most other things, your signal grows with the square root of time. Here it grows linearly with time. But still, if you want to wait, let's say 10 years, well, it's a bit long for a PhD thesis. But also you need a spectrograph that is stable over 10 years. And whose CCD and electronics and optical components don't degrade in the time scale of 10 years. So that is the observational challenge. And that's the reason why nobody has done this measurement yet. The LT should be able to do it, hopefully. I'll come back to that point. But so far, nobody has seen the universe expand in real time. But it is, as I just suggested, one of the flagship science drivers for the ELT. And in the case of the ELT, you can do these measurements optimally with the Lyman alpha forest, which also means that you can only do it from the ground beyond redshift 2, because below this redshift, you don't see Lyman alpha forest from the ground. And detecting the signal on its own, I would argue it's reason enough to do it. You're seeing the universe expand in real time. I mean, that's cool enough and important enough to do it just on its own merits. But you can also use these measurements to kind of close the loop of consistency tests and check whether your best fit model that comes from other data is actually correct. So the LT can do it at beyond redshift 2. At lower redshifts, the square kilometer array can also do it in principle, using a very different method, using emission lines rather than absorption lines, and stacking the signal from lots and lots and lots of galaxies, so a little bit like intensity mapping. So actually, measurements from the ELT and the SKA can be quite complementary, and I'll come back to that point. Now you can also go beyond this and say, well, I'm going to take a measurement of the redshift drift and use it to constrain cosmological parameters. So there you're sort of giving up the model independence, you're deliberately using it to constrain the parameters of any model of your choice. In that case, you can ask, well, how does this compare to other cosmological probes? The answer is, in principle, on its own, is not as constraining as other cosmological probes, like the CMB, for example, but it has the advantage of being orthogonal to it in many parameter space. So on the bottom right corner, you see a forecast that we did in 2012, for this is before Planck. So this is the usual omega matter versus W0 parameter, so matter density versus dark energy equation of state. And the blue contours that you see are the 1 and 2 sigma forecast constraints for Planck. And the red contours are the 1 and 2 sigma forecast constraints for the redshift drift. So you see that on their own, the constraints are a little bit weaker than the Planck ones, but they're basically orthogonal in parameter space. So if you combine the two, you get the green constraints, and you basically break the degeneracy between the two parameters. Now, in practice, you don't measure the redshift drift directly. You don't measure the equation of state in the middle. The equation in the middle of the slide. You measure spectroscopic velocity. You do this in velocity space. So what you measure is a delta V, but that is related to the delta Z or to the ZDT in a very simple way. So that's the equation that you see now. But the two, so the delta Z and the delta V, do have different redshift dependencies because the factors of redshift or 1 plus the redshift are not the same in the two cases. So if you can ask, for example, at what redshift is the drift signal maximally positive, and at what redshift is the spectroscopic velocity maximally positive, the answer is not the same for the two questions. The redshift at which the drift goes to zero, which is around redshift 2 for lambda CDM, you see it here, is also the redshift where the spectroscopic velocity goes to zero. So those two are the same. But this point is important. So the fact that the sensitivity to delta Z and the sensitivity to delta V are not exactly the same is important if you want to optimize a future sample of bright quasars for which you want to measure the redshift drift. Because then you can optimize your sample just to detect delta V with maximal statistical significance, or you can optimize your sample to constrain cosmological parameters using the redshift drift in combination with other data sets like the CMB, supernovae, etc. Because in that case, you can ask, at what redshifts should I do my redshift drift measurements to get constraints which optimally complement the constraints that I already have. So this is something that several of my students and I have been studying over the last few years. So in preparation for the LT, and we now have, I think, a fairly good idea of what the answer is and how to choose a sample of quasars depending on what your optimization criterion is. And I'll come back to this point in a couple of minutes. So just to give you a little bit of an idea, these are the sensitivity coefficients of the redshift drift and the spectroscopic velocity to several cosmological parameters. So I'm assuming a CPL parameterization for dark energy, so the usual W0, WA dark energy equation of state parameters that you see in cosmological papers. And what is plotted is the sensitivity coefficients as a function of redshift. So the derivative of the signal with respect to each cosmological parameter. So these are the derivatives that you have to calculate when you do a Fisher matrix analysis. So this is work of two of my students. Catarina Alves started this some years ago, and more recently, Mariana Meli Souza has been continuing this work. And you see several interesting things. So, for example, for omega matter, the sensitivity is monotonic, right? The higher you go in redshift, the higher your sensitivity to the matter density, which makes sense, right? Because you're going deeper and deeper into the matter era. But if you think of the dark energy equation of state, so if you think of W0 and WA, then the maximal sensitivity is around redshift 1. Again, it's a little bit different for the redshift drift or the spectroscopic velocity, but these functions are not monotonic. There is a sweet spot in sensitivity, which in principle you can explore. Now let me illustrate something I said before, and I'll do it again in a few minutes, but here's one example. So on the right, you see constraints on flat lambda CDM, so this is omega matter versus the Hubble constant, from a measurement of the redshift drift from the LT and from the SKA. And here, I'm assuming deliberately that I only have one measurement from the LT and one from the SKA, and I have absolutely no cosmological priors. So I just take the measurement, it gives me whatever it gives me, and I want to constrain lambda CDM. And the blue ellipse is what you'd get from the ELT with some assumptions on the amount of telescope time and so on, and some choice of redshift of the measurement. And the green ellipse is what you get from the SKA. And you see that the ellipses are really, really big in this parameter space, right? You can say a little bit on the matter density. You can say basically nothing on the on Hubble constant. But you can also see that the two ellipses are basically orthogonal in this parameter space. So the degeneracy direction changes with redshift. And remember that with the LT, we measure it at high redshift, so beyond redshift 2. With the SKA, we measure it at low redshift. So when we combine the two measurements, we immediately get a much more interesting constraint, both on matter density and on Hubble constant. So this is the power of combining high redshift and low redshift measurements of redshift drift. And this is a very important synergy between the ELT and the square kilometer array. Now, there's also another thing that you can do in principle. So with the canonical redshift drift, you're comparing some target redshift with redshift 0. So 0 redshift, so today is your baseline. You could also do what's called the differential redshift drift. So this is something that Ryan Cook proposed some years ago. And the idea is that instead of comparing to redshift 0, you compare with some other reference redshift, which is not 0. So the idea behind this, if we go back to this plot, is that with a standard redshift, you're measuring a difference, a spectroscopic velocity difference between some redshift and redshift 0. But since we expect the drift to increase and then decrease, if you think of measuring the difference between this redshift, so redshift around 5, and redshift around 1, where the drift is intrinsically positive, then the difference, the delta V, would be larger than if you compared it with redshift 0. So if you're limiting uncertainty, if your instrument has a minimum uncertainty in velocity space, having a larger delta V would increase the statistical significance of your measurement. So this is the idea behind differential redshift drift. Your reference redshift would not be redshift 0, but it would be some other redshift. And if you choose the two redshifts, so the nearer redshift and the faraway redshift appropriately, then you could maximize your delta V signal. And this is true in principle. Of course, you need to find quasars with absorption clouds at nicely placed redshifts, and that's up to nature. It's not up to you. Well, it's up to you to find them if you can, but it's up to nature to provide them to you. But on the other hand, the fact that you maximize the delta V signal does not necessarily mean that you increase your cosmological parameters by doing so. So again, this is the difference between delta V and delta Z. And if your optimization criterion is to maximize delta V, then that's one path for you. If your criterion is to maximize synergies with other probes when constraining cosmological parameters, then the answer might be different. So just to give you an idea that this is some work we're currently doing. So again, this is a sensitivity coefficient, like the ones I've shown you a minute ago. But now it's for differential redshift drift, so I don't have lines because the sensitivity depends on two parameter spaces, on two parameters in this space. So on the horizontal axis, I have the most distant redshift. And that most distant redshift can be anything between, let's say, 0 and 5. On the vertical axis, I have the ratio between the near redshift and the far redshift. And that ratio can be, for any choice of the far redshift, the ratio of the two redshifts can be anything between 0 and 1. So here I have the parameter space of all possible measurements of the differential redshift drift, where the farthest possible redshift is 5, and the intermediate redshift is anything between 0 and that one. So this might be a little bit of a difficult plot to interpret, but that's why it's saying. And I have the sensitivity coefficients, which are given by the color map. So the color in each plot is the sensitivity coefficient for each of the 5 parameters. So matter density, curvature, omega k, so Hubble constant, W0, WA. And the interesting thing is that if what you want is to maximize your constraint on omega matter, then the canonical redshift drift is your best choice because that gives you the best possible constraints. And this is basically just just a consequence of the fact that the sensitivity coefficient to the matter density increases linearly, increases monotonically, sorry, with redshift. So in that case, what you want is the highest possible redshift and compare it to redshift 0. But for the other cosmological parameters, that is not the case necessarily. And by choosing an intermediate redshift that is not 0, you can do better than with the canonical redshift. Now, you could also think of, so here I have sensitivity coefficients to each cosmological parameter. Sorry. But you could think, what if I want to maximize not just one cosmological parameter, but to maximize the overall constraints on this model? So then you need to choose some other figure of merit, and in principle, there's different ways to do that. That's something we're exploring at the moment. But my current guess is that you'll end up with something like the big plot on the right. So here again, it's the same kind of thing. So this is the distant redshift on the horizontal axis, the ratio of the intermediate and distant redshifts on the vertical axis, and the color map again tells you a sort of overall figure of merit for the full model. And basically, there's 2 islands where you get good constraints. So one is basically a distant redshift around 1 and compare this with redshift 0, so the canonical redshift drift. And that's basically because there you get really good constraints on the dark energy equation state. The other island where you get good measurements is a distant redshift, which is as high as you can possibly go to. Here I've assumed a maximum of 5, but if I extended this plot, this little island would also move to the right. And an intermediate redshift that is some small fraction of that high redshift. So here you see it's about 20%. So maybe this intermediate redshift would be around redshift 1. And you can understand why. So this way, you maximize both your constraint on the matter density and your constraint on the dark energy equation state. So at least, conceptually, this is how you choose your targets for the redshift drifts. Of course, in practice, you don't measure these things where you want to measure them. You measure them where you find bright quasars with clouds and at appropriate redshifts and so on. Okay, but let me come back to this point of synergies that I mentioned a couple of minutes ago. So, as you know probably, and I mentioned already, Andes, the successor of the espresso spectrograph for the ELT, is currently under construction. It's in phase B. A big consortium is building it. There's people in Brazil involved, including people in the room. So we're very actively studying synergies at the moment between various measurements that Andes can do, synergies with other ELT instruments, and also synergies between the ELT and other facilities. So here, so in this slide, I'm illustrating one of these synergies. So this is the work of Catarina Marx, which is a PhD student of mine. So here we looked at what you gain by combining Andes measurements of the redshift drift and Andes measurements of fine structure constant alpha, which I discussed in the previous days. So how can you constrain some of the models like the ones we discussed yesterday using Andes alone, so combining alpha measurements, which at least if we're thinking of class 1 models, will constrain dark energy as well. So combine measurements of alpha with measurements of the redshift drift. And this plot shows you a little bit of that. So at the bottom you have various figures of merit defined in the usual way in cosmology for 2 dynamical dark energy models. so to quintessence type models, essentially. One is a freezing model, so where the dark energy equation of state is approaching -1 today. Another one is a thawing model, where the dark energy equation of state is moving away from -1. And these are models where you assume a coupling to the electromagnetic sector, and therefore you have a varying alpha as well. And we don't need to discuss all the numbers in the slide, but essentially the bottom line of this is that with redshift drift measurements, you constrain some of the cosmological parameters, but you don't constrain the particle physics sector. In particular, you don't constrain this coupling zeta, which I introduced yesterday, which is the coupling of the scalar field to electromagnetism. With the alpha measurements, you constrain zeta and you constrain some of the cosmological parameters, in particular dark energy equation of state, but you don't constrain the matter density so much, for example. When you combine the alpha measurements and the redshift drift, then you get significant improvements in the constraints, and your figures of merit improve. And if you want to play with this kind of constraints, the Fisher matrix code that we use for this is now public. You can it's on GitHub. You can download it and play with it and do your own forecasts for this model or any other kinds of models. And you're welcome to contact us if you want any help on using the code and so on. There's also another thing you can do with redshift drift. So yesterday I mentioned briefly varying alpha cosmography. So expanding delta alpha over alpha in a Taylor series and constrain the coefficients of that series using alpha measurements. The redshift drift also allows you to do the standard cosmography that you do in cosmology, but in this case you can do what I would call real-time cosmography in the following sense. If you think of measurements of the SKA of the redshift drift, in principle, and if you're bold and if the SKA performs as well as people hope that it will do, with the SKA you can measure more than just the redshift drift that I've been discussing. You can actually measure the next derivative up. You can measure sort of the drift of the drift. And I'm not going to explain in detail how this is done, but in principle it's something that it's within the reach of the SKAs. It's not guaranteed at all that it will be able to do it, but it's within the realm of possibility. In any case, even if you cannot measure it directly, you can calculate a sort of numerical derivative. You can calculate the drift at two different redshifts, and then you can just by finite differences estimate a second derivative from that. That's of course not ideal. You'll lose some information when doing that, but it's in principle a possibility. So the reason, or one reason for this, for doing this, is that if you think of this, if you write the drift, so the first derivative that I've just been discussing in dimensionless units by dividing it by the Hubble constant, then you get something like this. It's just 1 plus z minus e of z, where e is just h of z divided by h0, so the dimensionless Hubble parameter. You can think of the second derivative, it would be like this, so 1 over h0 squared d2z dt0 squared. And if you imagine expanding these terms on the Taylor series, then something interesting happens. So just before showing you that, this is the plot of Z1, so the canonical redshift drift that I mentioned. It's just written in dimensionless units now, rather than centimeters per second per some period of time. So you get the same kind of behavior. This would be the behavior of Z2. So it grows from 0. And this would be a numerical derivative of the first derivative, a sort of dz1 dz. So this one starts not at 0, it starts at a value which is minus the deceleration parameter today, and then it decreases. And in each of these plots, you have three different lines for three different values of the matter density. So all these are flat lambda CDM models with different values of the matter density. So you can see that the cosmological parameters affect the signal. But the interesting thing is that if you Taylor expand the Z1 and Z2 that I've just defined, then so if you expand them to linear order, the coefficient of Z1 is minus the deceleration parameter, and the coefficient of Z2 is the next term up in the cosmographic series, which is a jerk parameter. So in principle, you can measure these terms directly, just from a slope in a plot, just by relying on redshift drift measurements. If you cannot measure Z2 directly, but you can measure the redshift derivative of Z1, then you get something like this. You get a constant term which is minus the deceleration parameter, as I mentioned, and as you can see more or less in this plot. So for omega beta 0.3 in flat lambda CDM, deceleration parameter is minus 0.55 today. So that's this minus Q0. And then linear term depends on a combination of deceleration parameter and the jerk parameter. And you can make some forecasts and ask, how well can you do this? And so there's a paper we wrote a few years ago, and with the specs, we assumed at that time, we found that you could constrain the deceleration parameter to 0.06 and the jerk parameter to 0.13. We're just finishing another paper looking at this in more detail, and we should submit it to a journal tomorrow, maybe early next week. We'll put it on the archive once it's accepted, but hopefully soon you should see some more detailed forecasts on this. But here I want to emphasize that the redshift drift is actually the optimal way to measure the deceleration parameter. And there's various papers making this point. Perhaps a clear one is a paper by Mike Turner and a student of his about a decade ago. Essentially, if you ask what is the best way to measure deceleration parameter in terms of giving you simultaneously good accuracy and good precision, the answer turns out to be redshift drift. I can explain why at the end if you want, but it turns out that this is the optimal way. And I also want to emphasize something which you may or may not know, even if you work in cosmology. Measuring the jerk parameter is actually an important consistency test of flat lambda CDM. So in a flat lambda CDM universe, this jerk parameter is exactly 1 at all redshifts. So the deceleration parameter changes with redshifts. All the terms in the cosmographic series change with redshift. But for flat lambda CDM, the jerk parameter is exactly 1 at all redshifts. So in other words, if you measure the jerk parameter at any redshift you want, and you find a value which is not consistent with 1, you have disproven flat lambda CDM. So this is an important, crucial test. And more broadly, and this is something that I also mentioned in the beginning, measuring a positive drift proves automatically that the strong energy condition is violated, and therefore it proves that there is dark energy. So again, this is an important consistency test, and to see a positive drift signal, you need to do the measurement at low redshift, so below redshift 1 more or less, so that is the realm where the SKA can do the measurement, the LT cannot go that low in redshift. Now let me illustrate another synergy between the SKA and the ELT for redshift drift measurements. So here I have again flat lambda CDM. So the previous forecast that I've shown you are basically relying on Fisher matrix analysis. This one is an MCMC. I'm not showing you all the parameters in this model. I'm just showing you the more relevant ones, with everything else marginalized as usual. And I want to draw your attention to the W0 WA plane. So this panel here. So the The greenish contours are the constraints that you get from the combination of cosmic microwave background and baryon acoustic oscillations. The yellow ones are what you get if you combine that with supernovas. And you see that there's a negative correlation between W0 and WA. The red contours are what you get from redshift drift measurements done by the SKA. So, and when I say the SKA, I should emphasize that I mean the full SKA, so the full configuration, not just phase one. So we need the full instrument for that. So full SKA plus the ELT. And what you see is that in this case, the correlation between W0 and WA is positive. So it's basically orthogonal in this parameter space to what you get from other probes. So again, by combining the two measurements, you can really pin down the behavior of the dark energy equation state. You also see that you don't get good constraints on double constant from the redshift drift. It's physically clear why if you think about it. So if you look at the definition I've shown you in the beginning, H0 is just a multiplicative factor in front of everything else, so it doesn't constrain, you cannot constrain it very well just by measuring drift. Okay, but all that being said, we're of course thinking of doing this measurement with the LT. We've done this, and one of the things we've been working on together with our collaborators in Trieste is to choose a sample of quasars for the redshift drift measurements by Andes, and we've come into what is called the golden sample. So it's a sample of seven quasars. So this mainly relies on the Kubrick survey, which Stefano Cristiani and others in Trieste and other places are actively working on. So this diagram shows you the known quasars, and I've plotted them as a function of spectroscopic redshift and the magnitude in the I band. So the bluish ones are the ones that were known before the Kubrick survey. The red ones are the ones detected by Kubrick's, and you see that there's a whole lot of them that were discovered. Some of them have been followed up spectroscopically, some not yet. But you see that there's so these seven that are circled, they're sort of outliers in a good sense, that they're very bright and they're high redshift. So these are our golden sample at the moment. So as far as we know, they are not lensed quasars. If they were, this would not be a huge thing. It would not prevent a redshift drift measurement in principle. One would have to be careful, but it's not a showstopper. But in any case, these are bright, these are high redshift, so these are the ones we want. And there's two here around redshift 4, which we are observing already with Espresso. Yeah, so this takes me to the Espresso redshift drift experiment, which is going on already at the moment. So as I emphasized, there's no detection of the redshift drift yet. So in fact, with current facilities, all you can get is upper limits, and the upper limits are 1,000 times bigger than the signal you expect. In other words, the error bar is 1,000 times larger than the expected signal, and of course these measurements are systematics dominated. So there's basically two such measurements or upper limits. There's one in the radio band done by Jeremy Darling, and that actually compares digital data with data from the pre-digital age. So as you can imagine, the systematics errors in that case are just huge, but it's a first attempt. More recently, Ryan Cook, when he introduced this idea of differential redshift drift, he tried to do one measurement, which is also an upper limit. So this one is done in the optical and at redshifts above 2. So you can read the papers and see how the measurements are done and how they analyze the data. So the Cook one is it uses data from the Keck telescope. Now, Espresso cannot detect the drift yet, but it can improve the current upper limits by a factor of about 10 with an experiment time of 1 year. And by experiment time, I mean the time between taking the first epoch of data and the second epoch. So going back to the analogy I mentioned in the beginning, you don't wait one night to look at quasar again, you wait 1 year. So that's the experiment time, 1 year. Um, and an observation time of 4 nights, basically 40 hours with espresso data. So we're going to look at two of these Kubrick's super bright quasars, as we call them. Um, our goal is to test the whole methodology for Andes, so test the pipeline end to end. So with real data, test whether the instrument is stable over this time period, test calibration. But we also use two quasars in different directions on the sky, but more or less at the same redshift, to also, well, first to see if the two results are compatible with each other, which they should be if the universe is homogeneous and isotropic, but also because if they are statistically consistent with each other, then we can combine the data from the two quasars and increase the signal by a factor of square root 2. And this is something that with Andes we will certainly have to do if we have 7 quasars, right? In the end, we need to combine the data. And that combination is also an important part of the pipeline. And ab initio, without doing it, it's not necessarily obvious what is the best way of combining the data. And so this is something that also needs to be tested with real data. So that's that's what that's several of the reasons why we're doing this. You could also think of this measurement as a first epoch for Andes. So you start taking data now, and then you observe those quasars again with Andes 10 years from now, and you already have data from 10 years previously. This doesn't gain you that much because the collecting area of the VLT is a lot smaller than the LT. So you gain a really small factor in photons, not a significant factor, but nevertheless, it is something that you might do just for the sake of it. And so for these two quasars, so the experiment is ongoing. For one of the quasars, we already have all the first epoch data. For the other, we have part of it. The rest is being taken now. And in the coming months, so we will be taking the second epoch data and we'll get a limit. So at the bottom, you see a first reduction of the data of one quasar. So this is basically 10 hours of espresso data in one UT mode. It's a beautiful spectrum. We're now modeling all Lambda alpha force and so on. Um, so the seeing, the observing conditions for this spectrum were great. The air mass was really small. So yeah, this is as good as a data set as you can possibly have with espresso, and we'll see what we get out of it. But then later on, we'll have the LT and Andes. And just as a small side note, we're currently writing, the Andes science team is currently writing updated version of the Andes science white papers. So there'll be 4 white papers, one for exoplanets, one for stars, one for galaxies, and one for cosmology and fundamental physics. We're finishing these papers right now, and the current plan is that they will appear on the archive and will be submitted to a journal in a few weeks, so before the end of November. So if you're interested in the LT and especially on Andes, watch out for those science papers. You'll be able to read them very soon. And the construction of Andes is a big international collaboration. So here's the usual slide with all the logos. I think it's more than 30 institutions from 13 countries, including Portugal and Brazil and many other countries. And for those of you who are students, there's chances of you collaborating in the construction of Andes and of course of using Andes and the ELT as a whole in the future. So I'm also a member of the project science team of the ELT, and if you want more information on the ELT as a whole, I'm happy to discuss this with you anytime, and because your generation will be the main users of the ELT, not my generation. But we're also doing other things with Espresso in preparation for Andes and for the redshift drift. And in order to detect redshift drift signal, a crucial aspect beyond collecting enough photons, for which you just need a big light bucket, so a big telescope, is calibrating your spectrum, right? Because you want to make sure that you do detect this signal, you're not simply detecting systematics or drifts in your spectrograph or the fact that your calibration sources change with time. So the stability of wavelength calibration is a crucial aspect of it, and including things like non-common path errors. Because if you imagine you calibrate your spectrum using a thorium-argon lamp or a laser frequency comb even, the optical path of those photons in the spectrograph is not the same as the optical path of photons from your quasar. In particular because photons from the quasar go to the atmosphere and the surfaces of the telescope, and the photons from your thorium-argon lamp or from your laser comb don't follow that path. So this could induce systematics in your data, and so you have to take into account all these possible systematics. So we're thinking very hard about ways of doing this and doing these calibrations. At the moment, we have installed an iodine cell in the optical path of espresso and trying to check whether having this iodine cell as a means of verifying this stability is feasible. So in other words, what we need to check, and this is a slightly technical point, but it might be worth for you to hear about it. We want to check how the LFC wavelength calibration is transferred to the calibration of a point source. So essentially, it's a transfer function that you need to measure in order to calibrate your spectrum. And so this is something that will have to be done to get a successful measurement. Another way of getting rid of these issues with non-common path errors, and this is something that people are starting to think about, is to use as a calibration source something that you put on a drone or maybe on a satellite in space, because then the photons from that source would also go through the atmosphere and the surfaces of your telescope, and then you'd not have any non-common path error. So all these are things that people are thinking about because, if we're going to measure the redshift drift with the ELT, we basically have to get everything absolutely right. If one of the steps in the pipeline fails, then we just won't detect the signal. We'll detect some other systematics, which is not nearly as interesting. Okay, so I'm just about to finish. Let me just give you a sort of outline of what the ELT could do for fundamental physics and cosmology. And indeed, the ELT could be an exquisite probe of gravity and fundamental physics. So you could use it to map the expansion history of the universe in a model-independent way through the redshift drift. You could test the weak equivalence principle with alpha data. You could test composition-dependent forces by measuring the proton-to-electron mass ratio in several different ways, as I mentioned earlier in the week. You can test the temperature redshift relation, distance duality relation. You can test the primordial abundances of light elements, so Big Bang nucleosynthesis. I didn't really have time to talk about this, but you can improve constraints on deuterium, helium-4, maybe even detect helium-3 cosmologically, so that there's a lot of progress there. You can do strong field gravity tests along the black hole in the center of a galaxy. Again, I mentioned this very, very briefly yesterday. But you could test the O'Hare theorem, for example, with Mikado. You can map the expansion history of the universe. You could use the ELT to do spectroscopic follow-up of very high redshift type 1a supernovas, which JWST detects, for example. So you detect them with JWST, and then you do a spectroscopic follow-up with Harmony, a spectrograph, Harmony instrument. You can constrain various other dark sector couplings, environmental dependencies, so dependencies on these couplings on local density. You could even test something like MOND, so in case you have heard of it, so there's modified Newtonian dynamics type models where the behavior of gravity is different in the low acceleration regime. And if you think about objects, so individual stars in the outskirts of our galaxy, then the gravitational acceleration of these stars is around the 10 to the minus 10 number that is the scale at which Mond effects crop up. So if you can observe these objects, which are going to be faint, of course, in the outskirts of our galaxy, where you have very weak gravitational fields and you can measure them, you can use high resolution spectroscopy to track their trajectories, then in principle you could do a direct astrophysical test of Mond. So this is an idea that some people are exploring as well. So most of these are science cases for Andes, but other instruments like Mikado, Harmony, and so on can also play a role. So then the question is, what do you need to be competitive? And all these science cases, basically, that I've been mentioning, are photon starved. So you definitely gain by having a big light bucket to collect the photons, but they're all systematics limited. So I mentioned, for example, that the previous results, the previous alpha measurements by Webb et al. Are limited by systematics. The espresso measurement that I've shown you is basically the first quasar measurement of alpha, which is limited by statistics, not by systematics. So now if we improve the statistics maybe by a factor of 10, just because you have more photons, but you do nothing about the systematics, then you're going to be systematics limited again. So you must reduce your systematics error bar also. So this is what I mean by photon starved by systematics limited. Collecting more photons is not enough by itself if you don't get a better control on the systematics as well. And this then, so in the case of Andes, means that for Andes to be a competitive instrument in the, so not competitive today, but competitive with other facilities 10 years from now, we'll need to improve the precision, the accuracy, and the stability of the spectrograph relative to espresso, and also improve the UV coverage. So espresso sees a lot less of the blue than the UV spectrograph, which is on the VLT, and this is a limiting factor for espresso, as I briefly mentioned. With Andes, clearly we need to be bluer than espresso to be competitive. So I think we need to push on all these four fronts to have a competitive instrument that can do really exciting science in this field in the 2030s. So this is up to the consortium and up to the scientists and engineers in the consortium. It's up to ESO to some extent as well. Other than that, what we need, well, depending on how much you want to do of the things in the previous slide, you need something between 50 and 250 nights of telescope time over the telescope's lifetime, so over 20 or 30 years. In some cases, you need to find better optimal targets, especially for mu. So for alpha, and I would say even for redshift drift, we already have enough quasars to keep ourselves busy. I mean, if we find even better ones, that's great, of course, but the ones we have are already okay. For things like mu and the CMB temperature, having some additional targets where you can do the measurements would be good, and some people are trying to look for them. And then for some transitions, for some measurements, as I emphasized, especially for measurements of alpha, you're comparing the wavelength of the lines in your spectrograph with the wavelength of these lines in the lab. And for some of these transitions, the limiting factor is the uncertainty of this wavelength in the lab. So this might seem amazing to you, but for some transitions, we can measure their wavelengths better halfway across the universe than we can do it in the lab. And the technical reason for this is that wavelengths that we measure at redshift 2 or 3 in the optical, in an astrophysical system, will be in the ultraviolet in the lab, and doing these measurements in the ultraviolet in the lab is technically complicated. So, but our experimental atomic physicists friends also should do some additional work on these to enable these astrophysical measurements. So this is another way of illustrating something I said in the beginning. This is a very interdisciplinary field. It needs contributions and efforts from a lot of people in a lot of different areas. And in one sense, it makes it challenging, but in another sense, it also makes it a really exciting area to work on. And I hope um, I managed to convince you about this a little bit. So just to summarize, what's the point? The acceleration of the universe tells us that our canonical theories of cosmology and particle physics are at least incomplete, maybe incorrect. There's new physics out there waiting to be discovered. And I've tried to emphasize the role of high resolution astrophysical spectroscopy in addressing this question. At the moment, if we think of varying alpha, nothing varies at the level of a few parts per million. And notice that this is already an extremely tight constraint. It's much more constraining than the constraints we have on dark energy equation of state. Is stronger than the Cassini bound on post Newtonian parameters and so on. So it's really tight in the overall cosmology context. Espresso is here, and new data, new constraints, new measurements will appear soon. So stay tuned. And in a longer term, the ELT and Andes has the opportunity to do a major contribution to this field and help us find this new physics that is out there. So that is work in progress. As I said, I find this a really exciting area with lots of things happening, and there's certainly a lot more work for a lot more people, and for you who are PhD students or master students and are getting into this field now. I think this is a really exciting time to be in this field. There's lots of work to do, so let's do it. And that's where I am. So thank you for your attention. And again, if you have questions now, please feel free to ask. But you're also very welcome to ask them later on Discord. So for those of you who are in the channel, I will keep the channel active for a year or so. So whenever you have any questions, just feel free to contact me there and ask whatever you want. Or just contact me directly by email. So the organizers at least have my email, and you're very welcome to pass it to the students if they want to contact me later on. So again, thanks very much. And if you have questions, please go ahead and ask.
Thanks. Let's thanks, Carl. Questions?
So first, thanks again for the very nice lectures. I have a question regarding to what level you expect that the constraints on the cosmological parameters from redshift that you will obtain from Andes will be more stringent than the one that you can obtain from other cosmological proofs like CMB or others.
Right. So if you compare the constraints on their own, they're certainly weaker. It depends on what fiducial model you assume, right? It depends on whether you assume just lambda CDM or CPL, so W0WA, or some more complicated models with more parameters. So, but generically, they are a bit weaker. But their usefulness comes from the fact that they're basically orthogonal in parameter space. So by combining redshift drift with CMB or supernovae, you're going to break degeneracies which otherwise you have. So this is the really neat thing about redshift drift. It's just because of the combination of parameters that you measure is different, and it also changes with redshift. It's basically different at low redshift and high redshift. It just so happens, and it's in a sense it's a coincidence, that it's pretty much orthogonal to the kinds of constraints we currently have, like supernovae and CMB. So I don't know if this was your question, but
yes, exactly. Thank you very much.
okay, so it's not that they're constraining them on their own; it's that you gain a lot by combining them with other constraints because they're basically orthogonal.
They break the degeneracies. Okay, thank you.
Yes, exactly.
More questions? Come on. That's it.
Carlos, so you presented a contours plot showing that the redshift drift measurements, the constraints from the redshift drift measurements from ELT and the SKA were orthogonal, right? And
Yes.
yeah, since they are measuring the same thing, the same in principle, I was wondering why they are orthogonal. So can you tell us how SKA is going to measure redshift drift? Because in the case of
Well,
ELT, I think I more or less know how this is going to happen. But in the case of SKA, what's different
right.
so that the constraints are orthogonal to ELT?
Yes. So okay. So the fact that the constraints are orthogonal is just a consequence of the fact that you're doing the measurement at different redshifts. It's not related to how you actually do the measurement. It's just
Okay.
the fact that the sensitivities to the various parameters change with redshift.
Okay.
So basically that, if you imagine, so I just had the two, so the ELT and the SKA,
Mm-hmm.
but if you imagine doing just one measurement at one redshift and plotting the ellipse at each redshift, basically the ellipse rotates as you change redshift.
Mm-hmm.
And it just so happens that uh, for the redshifts at which you do the measurement, for the ELT and the SKA, the two ellipses are basically orthogonal.
Okay.
And in fact, you can choose the two redshifts at which you do the measurement to maximize this orthogonality in a sense.
I see. So it doesn't matter if it's SKA or ELT. If you have two different measurements of redshift drift at different redshifts, and you put exactly on these two redshifts, you're gonna have orthogonal plots as well.
Yes.
Okay.
So this ellipse, if you assume you have a measurement at some
Okay.
redshift, regardless of how you obtain it, yeah, the ellipse just rotates.
Okay.
But having said that, let me take the opportunity to explain the difference of the measurement. So for the ELT, so this is a spectroscopic measurement, and in principle, it's one line of sight, right? So in principle, you could just spend some nights on one quasar and do the measurement there. In practice, for operational reasons, scheduling, etc., you're not going to do just one quasar. You're going to do some number of quasars, so 7 at the moment is our guess, so this golden sample, and then you're going to have to add the data from 7 quasars in some way. But in principle, it's a line of sight measurement. It's one direction. The SKA is completely different. So first, it's in emission, not in absorption, and then it's like intensity mapping in a sense. So you get this signal, so this 21 centimeter signal from billions of galaxies along a big patch of the sky, and then you basically stack all the signal, and you do this at two different epochs and subtract the two, and you see the lines shift by a certain amount. How exactly you do this in practice with a cross correlation function or something like that is not completely clear. So one difference is that for the ELT, there's a good number of reasonably realistic simulations of how you do the measurement. So Joe Liske did this in 2008, and I mean now we want to do it again for Andes, but in principle, people have thought about the details of doing this. For the SKA, there's no analogous simulation yet. And if someone there is working on the SKA and is willing to do some of these simulations, I think this is a really good project for a master's student or a PhD student to do these simulations in detail. Because now the hardware configuration of the SKA is a bit more clear, so these studies could be done. So yeah, conceptually is completely different. You stack information from a lot of directions on the sky. But this also means, so this is also the reason why in principle you could measure the second derivative. Or you could do the measurement separately in different directions of the sky, so in different patches, as long as you have enough galaxies in one patch, and then you could test homogeneity in isotropy, for example, which with DLT you cannot do because you just have one line of sight or very few lines of sight. So this is also something that the SKA could do in principle.
Thank you.
We have time for more questions. I'll give you a bit more time. Let me say something. It's pretty amazing to have resolutions that typically are used for exoplanet detections being used to study galaxies, right? Usually you are talking about kilometers per second, and if you look at the absorption lines, they have they have all these sort of internal movements that mirror the measurements, right? And I guess that's the reason we are going for quasar emission lines, which will be still large. So how I don't know if I missed it. How do you plan to handle the width of the emission lines, all these internal movements that probably, you know, that the devil is on the details. When you start to observe these sort of guys, I mean, all sort of new things will appear. So what do you envision that?
Yes. But here, so an important point is that when we're doing these measurements, so first we're using absorption, not emission, and second we're not measuring them at the quasar itself. We're measuring it in an absorption cloud
Oh, the
along the
forest.
line of sight of the quasar.
Okay.
Yeah. So that is precisely the point. Yes, in the quasar this is impossible, right? It would be too messy. There's no way this will work. And even in a low density absorption cloud, you need to satisfy yourself that you can do it. So for example, you have to check that these clouds for the redshift drift are following the Hubble flow, and that you don't have large peculiar velocities and so on. So you need to check that you are in shallow gravitational potentials and so on. And so in principle, this is not a problem. People have done this test, and this paper by Ryan Cook that I mentioned from 2020 actually discusses this a bit. So the effect of peculiar velocities is there, but it's at least one order of magnitude, maybe 2 orders of magnitude below the signal of the redshift drift. So in principle, that is not a problem for you. But you're right. The devil is in detail in these measurements, and even knowing, for example, the gravitational field of the Earth and how this might change with time, from spring to winter or something like that. This is important because you need to, of course, you need to correct for the movement of the solar system and all that. So you need to do this measurement in a cosmological frame, let's say, and not in the solar system frame. So all these things need to be worked out in detail. And as far as we can say at the moment, we believe they are under control, but you never know until you actually started playing with messy data and then you see what comes out, right? So this is one reason why we want to do this with Espresso. We want to do it basically end to end. So do all the steps in the pipeline because, if all goes well, we'll get an upper limit, which is 10 times better than we currently have, and that's what we expect to get. And if that is the case, then great. But maybe along the way we find some effect that we haven't thought about and which we'll have to correct for. So far I can tell you that to the extent that we have analyzed the data, everything is going as planned. So we're getting a result as good as we could hope to get, but we haven't finished. We haven't looked. We haven't gotten the second epoch data as yet. So we don't know. So, but I think 1 year from now, more or less, we'll be in a better position to say how feasible this is and whether we're confident that we can actually do this, or whether there's more work to be done and so on.
So I'll follow up. You choose a pointing that's sort of far away, some large scale structure, right? To avoid sort of the peculiar velocities and.
Yes. So also for cosmological reasons, for constraining cosmological parameters, you want the quasar at as high redshift as possible. Of course, if you go too high, then the quasars are very faint, and then you don't get enough photons. But this is the reason for choosing this, what we call super bright quasars. So they're reasonably high redshift and also very, very bright. Also, you get more, as you go to higher redshift, you get more and more of the Lyman alpha forest. And most of the signal for the measurement comes from Lyman alpha forest. The absorption lines, so the metal absorption lines, might contribute a little bit for the signal, maybe at the level of, let's say, 10%, 20%, something like that. But most of the signal will clearly come from Lyman alpha forest, which we have to model extremely well and so on. So yeah, the deeper we go in redshift, the more Lyman alpha forest we see, and therefore the better the signal in principle.
Amazing. So if we have one more question. The last minute.
Hi, Professor. My question is actually about yesterday's lecture. I was wondering about that alpha data that you were talking about, and how you mentioned that the scalar field easily couples, I mean, it can interact with other components. And then I was wondering if also this type of data could, and this field could be used to study like interacting models between the dark sectors, so like dark matter and dark energy, because I think you didn't mention it, but I was wondering about it.
Right. Okay. Okay. Yeah. I didn't mention it. It's true. So in principle, what alpha does, right, constraints for you is the coupling between the scalar field and the electromagnetic sector. Now, if you're studying interacting dark energy models, where that there's a coupling between dark matter or dark energy, you also expect a coupling to the electromagnetic sector. So you can also use alpha data to constrain models of that kind. So I gave one or two examples yesterday. So um, the uh, the runaway dilaton model that I mentioned is one example of this. So you have a coupling to dark. You don't have a direct coupling between dark matter and dark energy, but you have a scalar field coupling to dark matter in some way, coupling to baryons in a different way, so with a different coupling, and coupling to dark energy in yet a third way, so with a third different coupling, and also a coupling to electromagnetism. So yeah, if you're studying models where you have interacting dark energy, in principle, the expectation is that those models will also have a coupling to the electromagnetic sector, and therefore you can include your alpha data in your MCMC analysis uh, and use that to give you additional constraints. So how much more constraining this is with respect to constraints from cosmology will be model dependent, but it's certainly something that you can do. And I can explain you later if you want how in more detail all this is done. But yeah, in principle, it's certainly something that you can explore.
Okay, thank you.
So people got really excited at the last minute.
Hello, Professor. Thanks for the series of lectures. Uh, I have a question. Would a coupling of this type between a dynamical scalar field and electromagnetism, uh, wouldn't it be tightly constrained nowadays from collider experiments, and how those are already existing constraints? How do you take it into consideration in your analysis?
Okay. So this is a good question. It's something that I should have perhaps explained in the first lecture, but I didn't have time. So we know that these couplings run with energy, right? So in accelerators on the LHC, we see that alpha electromagnetic and the other couplings change with energy. So this is what particle physicists call running. So this is a high energy effect. Uh, the varying alpha effects that I'm talking about, so the coupling to scalar fields, is a low energy effect, which is additional to, so on top of the running effect in Latin accelerators. Because if you think of, let's say, if you have your the call just dropped. I'm not sure if it was this side or yours, but in any case, I'm back. Um,
Yes, yes.
so
I
I
think
don't
it
know
was
where
this
you.
side. We're back on the cell phone. So please go ahead.
Okay. Yeah. So yeah, I don't know where you stopped hearing me, but what I was saying is that the cosmological effects that we are studying are very, very low energy by comparison to the particle physics ones. So they're different effects. You could say they're independent effects.
Also, we just came back to finalize. Thanks again, Carlos, for a great. I still come on. Thanking you again for the great set of lectures, right? So people have your contact, Discord channel, email. If they have any follow-up questions, they can contact you. So thanks again.
Yeah.
And,
My pleasure. Again, apologies for not being able to be there in person, but please feel free to stay in touch and ask any questions that you might have.
So let's thanks Carlos again, and